So let's look at some examples of how to do calculations with the integrated rate laws. And the first thing you need to be able to do is recognize when you need one of these equations. Okay, and so the first thing you're always going to realize is that when you see a problem that mentions time and concentration, this is when you are going to use one of these integrated rate laws. Okay, so that's the first thing. So if we read this first problem, it says calculate the concentration remaining after 600 seconds. Okay, and so this essentially is a dead giveaway that you're going to use one of the integrated rate laws. Okay, that's really important because as you've seen, these kinetics problems start to blend together. So you need to be able to recognize you need one of these. Okay, and then the next thing you need to be able to do is figure out which one of the integrated rate laws to use. Okay, and so there's several ways that we might tell you that in the problem. One of the ways is it might just say in the problem, calculate the concentration for this first order reaction. Okay, so it'll tell you the order, and therefore you'll be able to select the integrated rate law. Okay, it doesn't do that in this problem. However, it gives us several other hints. Okay, so notice, first of all, that we have the regular rate law is given. And you might think, well, what is that for? Well, it might be useful, okay, in other ways, but it's definitely useful in telling us that this is first order, because as you can see, the concentration is raised to the first power, and it's a first order overall rate law. Okay, and we're given the K value, and this is per second, but normally we would see that written as seconds to the -1. So based on our little trick, we can figure out that that also tells us that this is first order. Okay, so either one of those things or both of them could tell us the order of the reaction. So since we now know it's first order, we're going to go ahead and use the first order integrated rate law. And you don't have to memorize the actual rate laws, but you do need to be able to remember which one is which when you see them on the equation sheet. So of course the natural log is the first order equation. So we're going to do natural log of A sub t is minus kt plus natural log of A naught. Okay, and so this is of course our initial concentration here, and this is our concentration at some time later on in the reaction. And so it's asking us to calculate the concentration of N2O5 remaining this amount of time after the start. Okay, and so which concentration is the unknown? So that's going to be our AT. Right, so we want to know the concentration sometime later on, and we're given the time, so we know that. So this is given. And we're given the initial concentration. Okay, so that is also given. Right, so all we need to do is plug in and solve for our missing variable, which is A naught. All right, so let's go ahead and do that. We're given K as well. So that's 5.2 times 10 to the -3 seconds to the -1. We're given the time, and I gave it to you in seconds. Okay, and notice that that's important because we want our rate law units to cancel out with our time units. So if I had not given you seconds, you would have needed to take the minutes and convert them to seconds. And A naught is the starting concentration or the initial concentration of the reactant. So after we do the math, we multiply the K value and the time to get -3.12. And we take the natural log of 0.04, we get -3.299. Okay, and then we can go ahead and add those two numbers together. And that gives us -6.339. And that's equal to the natural log of A sub t. Okay, so at this point, we do need to go ahead and solve for AT. And so we need to free our variable from the natural log. And so we have to take the inverse of the natural log, which is taking e to the x. Okay, and so e to the natural log frees the variable and gives us A sub t. And e to the -6.339 gives 0.00177, and then we do end up having two sig figs, so 0.0018 or 1.8 times 10 to the minus third. We're solving for the molarity at time t, so this would be the concentration units at the end. And it has gone down from 0.04 to 0.0018, so this answer does make sense. Okay, so let's look at example number 2. So the first order rate constant, so it tells us first order, so right away we know we can use the first order integrated rate law. Okay, so that's for the decomposition of a certain insecticide in water at 12 degrees is 1.45 years to the minus 1. Quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5.0 times 10 to the minus 7th grams per centimeter cubed. Okay, so notice we have concentration, different units than we're used to, okay, but concentration nonetheless. Assume that the effective temperature of the lake is 12 degrees. What is the concentration of the insecticide on June 1st of the following year? Okay, so first of all, notice that we're referring to time. Okay, time has passed, and we're referring to concentration. Okay, so that should lead you in the direction of an integrated rate law, and we're told it's first order. Okay, notice we're also told the temperature. Okay, and that's because remember your rate constant K varies with temperature. All right, so let's take a look at what we know. We know we're going to use this integrated rate law. And what do we know? So 12 degrees, like I said, that's just letting you know that we have the rate constant measured at the right temperature. Okay, what is this value? 1.45 times year to the minus 1. Which one of these variables in the equation does that represent? Okay, so if you said time, it makes sense that you would say that, but notice that it's years to the minus 1. And so obviously that's 1 over years. That's inverse of time. So it's not time, it's actually the units of our K value. Okay, remember that when you have K and it has time to the minus 1, that's indicative of a first order rate law. Okay, so this is just another clue that it's first order, but this is also our K value. So we know K. What is time? Well, let's see. What is the concentration on June 1st of the following year? Okay, so how much time has passed? 1 year. So we know T is 1 year. And then we also know the concentration. We know one of the concentrations. So which concentration would this be? Well, reading the question carefully, that's going to be our initial concentration because we want to know what the concentration is in the following year. So at a later time. All right, so we're trying to figure out AT. Okay, so our rate constant K, our time, 1 year, notice those cancel. We're adding the natural log of A naught, which is 5.0 times 10 to the minus 7th. Oh, and notice that even though we have these strange units of grams per centimeter cubed, we don't need to convert those to molarity unless the final answer needs to be in molarity. Okay, so we can go ahead and express our answer in these same units, our final answer in these. So let's go ahead and do the math. Okay, so if we take the natural log of 5.0 times 10 to the minus 7th, that gives us minus 14.509. And then we just take e to the x on both sides, take the inverse of the natural log, and that gives us 1.17 times 10 to the minus 7th grams per centimeter cubed. And so notice now, of course, our concentration has dropped. So it's gone from 5 down to 1.17. So in this case, we're being asked something slightly different. Okay, so first of all, it's saying how long. Okay, and so our unknown here is, of course, time. Okay, what amount of time will it take for the concentration to drop to this concentration here, all right? And so that's going to be which A? Is that the initial, or is that A at some time t later on? Okay, that's going to be A at some time t later on. And we already have one unknown, the time, so now we need to think about, well, what was our A naught? Okay, so this problem's a little ambiguous because it could be two different things. It could be this concentration that we just calculated, could be our A naught, or it could be the original concentration up here in the problem. Okay, well, let's think about it. Could it be this A naught? Well, this is actually a lower concentration than this one, so it can't be this one that we just calculated that they're thinking of in the problem. It must be the other one. So this is our A naught, 5.0 times 10 to the minus 7th grams per centimeter cubed. Okay, and we still know our K value that was given in the problem. It's the same K, we're still at 12 degrees, all right, presumably. All right, so now we're solving for time. So we could use the same equation that we just did up here, or we could use the other form of the first order integrated rate law. And I'm going to go ahead and use that one just to show it to you, and also because it's convenient. We know both AT and A naught, so it's convenient just to solve for them over here on the left-hand side. And then we know minus KT is our equation. So remember, this is completely the same equation, it's just rearranged algebraically from the one above. So we just plug in our AT and our A naught. They have the same units, so those units just cancel out. I just canceled them out already. K is 1.45. T is our unknown, because we're trying to find out how long it's going to take for the concentration to drop. Okay, so taking 3 divided by 5 and taking the natural log gives us minus 0.5108. And that's minus 1.45 years. I'm going to go ahead and solve for t. We're going to divide both sides by minus 1.45 equals 0.35. And then notice here, years to the minus 1 is the same as 1 over years, right? And so we have 1 over years. And so just like 1 divided by 1/4 is 4, 1 divided by 1 over years is years. So if your number or variable is in the denominator of the denominator, then it ends up going up to the top. It's on the bottom of the bottom, it goes to the top. So 0.35 years is our time. Now, of course, we don't ever talk in those terms, but that's about 1/3 of a year, or approximately 4 months. But in this problem, it's just asking us for time. It doesn't specify what units, and so we can go ahead and leave that in years. Okay, so let's look at another example. We're given a rate constant. We're asked how long in seconds would it take for the concentration to decrease. Okay, once again, time, a specific range of concentrations. That tells us integrated rate law problem. So look for time and concentration. And so now what's easy to do is we've been doing a lot of problems with the first order integrated rate law. So it's very easy just to start writing down your formula, plugging in. But you need to be really careful that you're paying attention to whatever information is given to tell you the order. This problem does not tell you that it's first or second or zero, but what does it give you? The rate constant units. Okay, so this is K, right? Rate constant is K. The units are molarity to the minus 1. Remember, you're going to add 1 to that, basically, to the absolute value of the molarity power, all right? But anyway, so this tells you it's second order. Okay, so if that was molarity to the minus 2, it would tell you it's third order, etc. And so we need to make sure and use the second order integrated rate law, or we're not going to get the right answer. All right, so let's go ahead and write that down. So remember, that's the one where you have the inverse variables. You have positive KT. Okay, and so from here, we just need to plug in and do some math. So take a moment, which one of these concentrations is AT and which one is A naught? Okay, so hopefully you're saying that this is our initial concentration. okay, because that's what we're starting with. It's from this to that. Okay, so this is our AT. The one later on is lower. Okay, it's another way to tell. All right, so we're going to go ahead and plug those in. 1 over 0.28 molar equals K, which is given up here, 0.54. Molarity to the -1, seconds to the -1, plus, okay, careful about that, 1 over A naught, and that's 0.62. Okay, and just because the algebra is a little different on this one, I'm going to go ahead and run through it. Okay, so 1 divided by 0.28 is 3.57. Molarity to the -1, oops, times our time, plus, there we go, 1 over A naught, 0.62. All right, so we have times time, so we have our variable in there, kind of important. And 1 divided by 0.62 is 1.61. Molarity to the -1. Okay, so now we're going to go ahead and start isolating variable t. Very important to notice we're adding here, and so we have to subtract. I know some of you are algebra aficionados and masters. Okay, so don't roll your eyes, but I know that a lot of times people have forgotten some of this math, or they're just not that fluid with it, so that's why we're going through this. Okay, so this gives us 1.96 equals 0.54, molarity to the -1, seconds to the -1 times t. Okay, so at this point, we just need to solve for our variable t, so we're going to, now we can go ahead and divide. Units and the numbers cancel, the molarity to the -1 cancels, and we end up with t equals 3.62, but we'll go ahead and leave it with 2 sig figs, and then it's 1 over seconds, which of course is 3.6 seconds as your final answer. So notice we were trying to solve for a time, and we got a time with time units. Okay, so it's really important to track those units. It can kind of reassure you you're on the right track. Okay, so the main reason I showed you this problem was to remind you of some of the math, and then also to remind you that you have to identify which of the integrated rate laws you're using for a problem. So this one happened to be second order. So if you did this with natural logs and used the other equation, you'd get a completely different answer, and it would not be correct. Okay, so just really important. All right, so let's look at one more kind of twist that you'll see with some of these problems. Oops. And that is problems that are presented in this fashion. So let's just kind of look at this. The conversion of cyclopropane to propene in the gas phase is a first order reaction. You like that? It's telling us the order. With a rate constant, okay, given, notice first order units at 500 degrees. How long in minutes, okay, so we want to know time, will it take to convert 74% of the starting material? Okay, so this is a little bit different with regards to these integrated rate problems. We definitely have time, and we have a percentage. So we're not really talking about concentration per se, but it's sort of related to concentration. It's related to amount. And here's the way to think about these problems. When you're given one like this, you need to, we know we're getting rid of 74%. So let's just assume a starting concentration. And we could use anything we wanted to. We could use 7.796 times 10 to the -4th. As our initial concentration. We could use 1,000,000. We could use whatever we want to, but it makes a lot more sense to use something really simple that we can easily determine what 74% of it is. Now, you could, theoretically, and it would work, assume 100 molar, right? But the problem with doing this, it's just a little conceptual thing. It's almost impossible to have 100 molar of anything. This is way too high. So rather than assume 100, let's go ahead and assume 1 molar. That's much more realistic, okay? 10 molar is more realistic, but 100 is silly. Okay, so if we assume our initial concentration is 1 molar, and then it says, how long will it take to convert 74%? So does that mean that we have 74% left? Or does it mean that we've used 74%? Okay, well, it means that we've used 74%. Okay, so the wording on these, you have to really pay careful attention to. So we've used up 74%. So that means that, well, what's 74% of 1? 0.74. See, that's why we chose 1, because it's easy to think about the percents. Okay, so 1 minus 0.74 is 0.26. So this is what we have. After we've used up 0.74, we have 0.26 molar left. Now, this is only one way of phrasing the problem. It could say something. How long in minutes would it take for 74% of the starting material to remain? And if we have 74% remaining, that means that AT would be 0.74. Okay, so you have to pay attention to the wording. All right, so we now know, though, we have an A naught, we have an AT, we have a K, okay, because that's the rate constant. And so let's go ahead and calculate the amount of time in minutes. And we know it's first order, so we can use our first order integrated rate law. And this is the form you really should use. It's the most convenient. Whoops, that's a T, that's a naught. It's the most convenient one for these kind of percent problems. So natural log of AT, which is 0.26, over A naught, which is 1. Okay, so you can just leave that out if you want, or you can put the 1 in, whichever floats your boat. And then minus K is 6.7 times 10 to the minus 4th. And then you just plug and chug to your heart's content. Natural log of 0.26 is minus 1.347, and then we just do our normal algebra. Divide by both sides. (2011) if you round up there, and it's 1 over 1 over seconds. You have seconds to the minus 1 in the denominator, so that ends up as seconds here. And then, of course, that's way too many sig figs. We have 4 sig figs here, so we could just go ahead and round that to 2. So we could say 2.0 times 10 to the 3rd seconds. And I am all finished, right? No, okay? You want to make sure you've noticed that the answers needs to be in minutes in this case, and so then we just have to say, well, in 1 minute, there are 60 seconds. So this is about 34 minutes. So this format of presentation where it tells you the amount that's being converted or that's left is really common in nuclear decay problems. And so if you happen to see any of these kind of problems, it'll talk about the nuclear decay of an isotope. So essentially, when you have a radioactive substance and it breaks down through alpha or beta decay, that kind of nuclear decay is always first order. And so, and they sometimes will not tell you that in the problem. So that's another thing you can assume when you see problems where the nucleus is, you have radioactive decay, that's going to be first order, and you can use this kind of a setup.